Hi, everyone. This is Yang from UC Santa Cruz Computer Science Engineering, and I'm going to present our paper, Fair Classification with Group-Dependent Noise Labels. The main takeaway of this paper is the hidden label noise or the hidden label bias can be harmful, but they can be overcome by robust algorithm designs. And in this presentation, I'm going to tell you what are the possible harms and how are we going to mitigate these harms. Our paper considers this standard fair classification setting, where we are trying to find a classifier H that maps the feature X to label Y. And we're going to focus on binary classifications where the Y can be either -1 or +1. The goal of us is to find a classifier that minimizes the expected 0-1 prediction errors on this distribution D, the clean distribution D. But simultaneously, we want the classifier H to satisfy a set of fairness constraints. Let me read the constraints to you. So here I'm going to use Z to denote the protected sensitive attributes. So the lowercase z and z prime, you can consider these two quantities represent different gender groups, different racial groups, or different age groups. For each of the Z and also for a given classifier H, the function f denotes a fairness metric. But there are different ways to define the f, depends on the application of the setting. But typical ones include the f represents the true positive rates of the classifier achieved on the group or the false positive rates. And this question can be solved by this so-called FAIR ERM or FAIR empirical risk minimization framework, where the algorithm itself will receive a set of training data that are in tuples of xi, y, zi. And then the opportunity function will be approximated by the empirical losses incurred by classifier H on this training data set. But we can also empirically compute the fairness constraints on this data set. So here I'm using F tilde to denote the empirically calculated fairness measures. So for instance, when we are computing true positive rates, this is basically counting how many examples we're predicting positively among all these positive examples. The case we're interested in is when the clean data is not available, but instead we have access to a noisy training data set that are in the form of xi, y tilde, and zi. So we call y tilde as the noisy labels. And the y tilde can be different from the true y. And we use the following error flipping model to capture how different and how likely y tilde will be different from the true label y. And particularly, I'm going to use E plus E minus to represent the likelihood of y tilde differs from yi, depends on if yi equals +1 or -1. And we allow this error rates, E plus E minus, to be different across different groups. So E plus E minus are functions of group Z. So this is what we mean by group-dependent label noise. And then the goal of this FAIR ERM is to train using only accessing this noisy training data set. This is something I think that can basically happen in any case that involves human annotations. The popular ones include image labeling, or in healthcare when we're using diagnosis to train classifier or to train predictor. But here I'm also studying a recent paper by Drassel and Farid, shows that when we're inviting human agents or human participants to help us evaluate build decisions, the human agents are making systematically higher annotation error or prediction error for one racial group than the other ones. Okay. So first, what are the harms introduced by label noise or label bias? By that, I mean, what's wrong with using the noise label y tilde blindly? And by blindly, I mean, we're going to plug in the noise label y tilde into the FAIR ERM directly. So we're going to use the noise label to evaluate the losses, but also we are going to compute the fairness metrics on these noisy labels. Okay. And for the rest of the presentation, we are going to call these fairness measures calculated on the noise labels as the perceived fairness, because these are the direct fairness metrics we computed using this training data. So first of all, in terms of training error, we show that memorizing noisy labels can be harmful. In here, I'm demonstrating this harm by a 2D synthetic example. If you look at the left-hand side, we have the clean case. We have two classes, where the inner group corresponding to one class and the outer group corresponding to the other class. So for the clean case, the training question is very easy. So here I'm showing the descent boundaries of the classifier, and they separate these two classes perfectly well. But from left to the right, I'm adding 20% label noise and 40% label noise. You can see the discern boundary becomes less and less confident. So here I'm using color bands to denote the prediction confidence of the region of different regions. And this is exactly because of the existing of noisy labels, and the classifier may be confused by conflicting labels for similar examples. So we actually have a more formal and rigorous way of summarizing the harms of memorizing noise labels in the following paper. So for people who are interested, here is the archive link. More relevantly to our fairness question, the other harm is training with noisy or biased labels is going to return a classifier that appears to be fair, but it actually not. So again, I'm demonstrating with this very toy example where I'm having two dimensions of features, x1, x2. So, and each of the feature takes a binary value being either 0 or 1. So 2 by 2, we have 4 possibilities. And we have two groups of people we are trying to protect, group A and B. For each of the x, depending on if x is coming from group A or versus group B, the true label y or yb can be different. So in the first column of the table, I'm summarizing the basic statistics of this distribution data. For group A, suppose we managed to collect 400 training data points, so 100 for each of the 4 cases, and all of them are correct. So if you're comparing these 400 labels with the YA, they're all correct. But for group B, 25% of group B's training labels are incorrect. So here I'm highlighting the incorrect labels for group B using a different color. And in the last column, I'm showing the pool data. So this is the data summarizing the data coming from both group A and B. And we are going to train a classifier on this pooled data. So this is the entire data set we have. But at the same time, I'm going to enforce equalized true positive rates on this between these two groups. And the resulting classifier is listed in the very last column, which I call H star fair. Okay. So if you compare these predictions of H star fair with group A's data, okay. So if you come back to the group A's data, we have 200 examples having positive labels. Among these 200 examples, H star fair is predicting exactly half of them correctly. So we are achieving 50% true positive rates on group A. But also, if you compare H star fair with group B's data, again, the first column under group B, we also show that H star fair is predicting half of these points correctly for group B. So it seems like on this training data, H star fair is fair because it has equalized true positive rates. However, if you compare H star fair with the true label listed at the very beginning, okay, among the 3 positive cases of group B, H star fair is computing or is predicting 2 of them correctly, returning a 2/3 true positive rates. While for group A, of the 2 cases of the positive labels, we are only predicting 1 of them correctly. So H star fair actually has a much higher true positive rates on B as compared to A. Okay. And the last experiment show when we combine the learning objectives with this perceived fairness guarantees, meaning the fairness metrics, all the fairness constraints computed on the noise labels, we can even do harm to the accuracies, meaning the fairness constraints on noisy labels will lead to accuracy drops. So here we did experiments on the adult data set where we added label noise to the female group. So here we have male-female groups we are trying to protect. In this table, on the right-hand side, I'm listing two classifiers. Again, on the left, I'm listing the F, where F is trained on this noisy data set, but without adding any fairness constraints. So this is this is trained by unconstrained optimization. On the right-hand side, we are training classifier F fair by adding equal true positive rates and false positive rates constraints. And we do observe that by adding this wrong fairness constraints, the false positive rates for both of the groups increase significantly. So this is indicating a significant drop in the performance. And the male group's accuracy dropped substantially from 80% to 73%. Okay. So in our paper, we also formalized some of the observations by theoretically proving that the perceived fairness does not imply true fairness guarantees. So particularly, we showed that when we're equalizing the perceived true positive rates and false positive rates defined on the noise labels. Again, so here I'm using tilde TPR to denote the TPR computed on the noisy labels. Okay, so when we're equalizing the perceived fairness metrics, the true fairness gaps in TPR and FPR remains largely positive, according to the following formula. Okay, this solidates our argument that the perceived fairness guarantee does not imply true fairness guarantees. But we do notice there's a corner case when the error rates are homogeneous across different groups. It seems like equalizing the perceived fairness metrics suffices to guarantee the equalized true positive rates and the real false positive rates defined on the Klein distribution. But for the generic heterogeneous cases, the gaps in the true positive rates and false positive rates are remaining positive. So I'm going to quickly review our solutions. We provide two solutions in this paper. Both are inspired and also extended existing solutions in the learning with noise label literature. The first challenge we have in this extension is we need to account for group-dependent label noise. So most of the existing works assumes the error rates E plus E minus are homogeneous across different examples, but here they can be different. Second challenge, most of the solutions focus on the unconstrained ERM framework or the unconstrained optimization question, but here we need to handle the constraints. And lastly, because we need to repeat this the procedure for different groups, I'm going to explain to you later, we want an efficient error rate estimation procedure or solver. Again, I'm going to explain why. So the first solution we build upon is called loss correction. So loss correction defines a surrogate loss in the following way. Instead of using the noise label y tilde to evaluate a prediction T directly with the loss function L, we are going to define a corrected loss. Here I'm using LC to denote this corrected loss, which is a linear combination of two losses. The first loss is, again, the loss is defined on the noise label y tilde, but then the second loss is defined on the opposite of the noise label, minus y tilde. So this is to consider the case where the y tilde can be different from the true labels. And the linear coefficients are depending on the knowledge of E plus E minus. And I'm going to tell you why the coefficients are defined in this way. With defining the corrected loss in this way, basically we can perform ERM with this with this corrected loss summing over all these training data points. And the reason we are using these coefficients to do the linear combination is because we can show that the corrected loss or the surrogate loss is an unbiased estimation of the true losses when you're taking the expectation with respect to the distribution of the noisy labels. But again, to apply this approach, we need to know E plus E minus. And in this paper, we detailed an existing approach from the literature, but in the context of our paper. This is based on the notion of anchor points. So these anchor point methods tries to find samples that we can estimate to belong to a particular class highly likely. Okay, so based on these sample points or based on this estimation, basically we can use these samples, these confident samples, as proxy of the ground truth labels. And then we can use the noisy labels on this subset of samples to calculate the error rates. And then we need to repeat this for every single group, say. This approach, the success of this approach depends on how many anchor points or how many confident points you are able to find. But we've also provided an alternative approach in the following GitHub link that uses a high-order consensus approach that does not require anchor points. And the second approach builds on this notion of consensus among a local cluster of similar points. Okay, take a look if you're interested in this. The second approach we build upon is a recent loss function we proposed from our group. This is loss function defined across multiple samples, and the implementation of this pure loss does not require the knowledge of error rates, E plus, E minus. So it's relatively easier to implement. The high-level idea is shown in this figure. So when we're evaluating XR via tilde, we are also borrowing a pure samples P1, P2. So P1, P2 are entirely different samples to help us evaluate the classifier. So the basic intuition is, while we are training the H to learn something from these pairs of XR via tilde, we want to use P1, P2 to punish H from overfitting to the noisy label distribution. Because H shouldn't be predicting correctly on XP1 against YP2 tilde, because they're coming from a different pair of samples. Okay, so therefore the pure loss is first evaluating the losses on the same pair of examples minus the evaluation on the different pairs of examples. But we noticed that in order to apply pure loss in our setting, we need to reweight pure loss to account for the difference of the error rates across different groups. This reweighting parameter, which we denote as delta ZI here, has a form of 1 minus E plus minus E minus. This basically captures how much noise this group has. And again, we can leverage existing estimation techniques to estimate this delta. But we just want to mention, estimating this delta is much easier than estimating the E plus E minus, these two quantities separately. Okay, with this, we can plug in the corrected loss or pure loss into the ERM framework, along with the corrected constraints. So I'm omitting the details here, but basically based on the lemma I showed you earlier, like how perceived fairness relates to true fairness, we can correct these fairness constraints too. And it turns out it's sufficient to know the knowledge of delta Z, the one I showed you earlier, is sufficient to help us to correct these biases in the constraints. Okay. So quickly, some empirical evidences. We have a substantial set of empirical evaluations in the paper, and also discussions. But first of all, this is the distance boundary I showed you earlier. But now with pure loss, the distance boundary holds up pretty tight. So this is evidence of pure loss doing the right thing in terms of defending against label noise. But also we deliver a set of fairness studies across different data sets for different protected groups. We compare our approaches with the corrupted model, meaning training with the noisy training data set directly. Okay. So we show substantial comparison studies that first shows that if you look at the middle of the table, the corrupted labels consistently incurs high fairness violations as compared to surrogate loss approach or pure loss approach. Our fairness violations are capped to a relatively much smaller level. We also compare our approaches, evaluate our approaches across different noise rate and different noise regime. Again, if you look at the last column, this is a group pure loss, has consistently lower fairness violations. This shows the robustness of the approaches we propose. Okay. So this paper cautions the harm of training with systematic label bias and we provide solutions for learning with these noisy labels when enforcing fairness constraints. In the future, we are developing training methods to handle more complicated training noise settings. And also, we are trying to protect the training against other sample biases in the training data. If you have any questions, feel free to email us. And also, we have a live session to answer your questions. Hope to see you there. All right, thank you.